Good afternoon, everyone. This is spring of 2020 College of the Sequoias College Algebra course. We are covering applications of exponential growth and decay. In the book that we're using, it's section 4.6. 5, section 4.6, applications of exponential growth and decay. So I'm going to start off with one from physics. We have Newton's law of cooling. So this is how much does the temperature decrease in a material that is above room temperature or above the temperature around it. Generally, we're assuming something like room temperature. Temperature goes with T. And the equation that governs it is the final temperature equals the initial temperature plus a cooling factor times e to the negative kT. T is lowercase, or so big T is temp, little t is time, and K is a cooling rate that is specific to the material for a given material, and usually what we're solving for. When we're solving these, that's the one we're solving. Once we have it, we can start figuring out final temperature after a given amount of time, no matter what the product is. So let's just look at how we'd go through solving this. So take a note of that. So I've got T final, I'm going to say TF equals TI plus CE to the negative KT. We want to isolate our exponential. So we'll subtract TI from both sides. You have T final minus T initial equals CE to the negative KT. We divide both sides by C, which is just the coefficient on the exponential. And we get TF minus TI over C equals E to the negative KT. How did we get rid of E in the past, in the last section when we were going over solving these? We take the natural log of both sides. This becomes natural log of T final minus T initial over C equals, we can pull the negative KT down, and now that's times the natural log of E. And we know that's 1. Often they've gotten data for a given temperature, the starting temperature, counted how long it took, and found the temperature after a certain amount of time. They know T, they're just solving for K. So divide both sides by negative T. And k equals -1/t natural log of t final minus t initial over c. I'm sure there's a problem in the homework that gives you values for those. You can plug them in there, but that's how we go through and solve those. Okay? That's only slightly different than the main exponential growth and decay problems. The basic ones we start off with for exponential growth and decay start off in this form. We have y equals y naught e to the kt. That's the general equation. If k is greater than 0, we have growth. If k is less than 0, we have decay. K greater than 0, population models, bacteria models, like petri dish, stuff like that. K less than 0, we have things like radioactive decay, carbon dating or half-life. This is how they date really old stuff. And the other thing we have for population models, continuously compounded interest. We looked at that briefly before. In that final model, we said A equaled P0 e to the RT, so R equals K. Same formula. So if you've been paying attention to the news, I think I've posted it already. I will share with you an article on the coronavirus that shows the mathematics behind it. In fact, I can show it to you real quick. So this is the math behind it. This was data as of March 28th. And the model they use has something going on like this. These all have different values. Notice we have an exponential in here. It's in the denominator. If it were on top, it would be positive. And that ends up, that's why we end up having exponential growth. These other terms help flatten it out. And you can go through and read it. It talks about the data from China and inflection points that we've talked about before, but you'll learn in calculus. It's where the graph changes. It's been a big word in the news lately. But the real way of looking at it is the number of daily new cases or daily new deaths. It's when that stops going up and starts generally going down. Deaths follow the same curve, though. And so this also has stuff for the US, and we have not reached the flattening out point yet, or the inflection point. If you look at the calculus-based one, they suspect it's going to be in the next 10 days. Most of the country will start hitting that inflection point. Maybe two weeks. But let's take a look at something else that was in the news. 2020 is our current year, and every decade they do this census. So let's set up a problem. At some point in 1999, the world hit the 6 billion people mark. By the end of 2020 or 2010, it had exponentially grown to 6.947 billion. Let's find the growth rate. Okay, I'll leave that up for a little bit so you can write it down. Okay, so we're going to do that y equals y naught e to the kt. Y naught is our starting value, 6 billion. Y is our ending value. So start, finish. 6.947 billion. T is time. So we ended in the year 2010. We started in the year 1990. I said 1990. This should have said 1999. Got a little sloppy there. Is 11. We don't know what time it was in the year 1999. We'll just go give it the full year. It doesn't make a huge difference at this point between 10 and 11. And so let's plug in what we've got. We've got 6.947 billion is that equals 6 billion e to the k times 11. We'll divide both sides by 6 billion. Because we were trying to get the e alone. Isolate our exponential. Of course, that's 1 here. The zeros cancel like that. We've got 6,947 over 6,000. I don't think it simplifies much more than that. Equals e to the 11k. And then how do we deal with that? Take natural log of both sides. We can pull the 11k down. And we have natural log of e, which we've seen repeatedly is 1. We divide by 11 and we get k. What is that value? Let's find out. That's the natural log part. Then we divide by 11. And we get approximately 0.0133. I'm going to write them all. It's still approximation because the calculator doesn't, it's an unending number. If it had been at the end of 1999, we could argue 2000. If K had been 10 or T had been 10. This doesn't change much. We just change the T value. And I can just take that last answer and multiply by 11, divide by 10. See, not a whole lot different. So it depends on what time of the year that actually happened. And what do we use this for? For with a given K, with the K computed, we can calculate the time for a new ending population. Or we can calculate what the population should be, or the population after a given amount of time. Okay. Any questions? So email me. I'll try to make a follow-up video for you. A lot of these follow the same idea. So let's see. Ian finds an interest rate of 2.25% with continuously compounded interest. How long will it take for his money, or how long will it take for a single initial deposit to double? So he just puts the money in the account. He doesn't touch it. He just wants to, how long will it take to double? Assuming the interest rate stays the same, it should. You tend to lock in interest rates when you put it into like a certificate of deposit or something like that. So what do we have? Well, I didn't actually say what his starting amount was, did I? Let's say his initial deposit. He's really happy he's doing it. It's smiley face. Smiley face dollars. Variables don't have to be X. The X is a placeholder. Smiley face is my placeholder here. So if he doubles his initial deposit, a doubled investment, how much does he have? He now has two smiley faces, dollars. So again, we start with y equals y naught e to the kt, or we also had a equal p naught e to the rt, k equals r. Both of these equations are the same. The zero subscript says initial part, and the left side is the end. final part, just like the Newton's law of cooling one. So in this problem, he ends with 2 smiley faces. He started off with 1 smiley face, and he had E, K was 2.25%. We want that as a decimal. We move the decimal left twice. 0.0225 times T. Interestingly enough, we divide by smiley face. If you don't like smiley face, you can use X. We get 2 equals e to the 0.0225 t. Again, take the natural log of both sides. We pull down the exponent. Times natural log of e, which is 1. And we divide by our 0.0225. And we get t equals the natural log of 2 over 0.0225. How long is that? Remember, t is in years. Natural log of 2 divided by 0.0225 takes a while. Considering he didn't have to do anything to make it double, but just let it sit there, 30.8 years seems pretty good. What was this value right here, though? What is that? That was K. The 2 came from double. So I'm going to pause. I want to point out what this does. You can expedite this problem quite smoothly. Notice the time ends up being the natural log of the multiplier times your of your deposit divided by the interest rate. What if K had been, and you don't find this, what if K had equaled 0.0525? And then our time would have been natural log. He still went with double equals 2 over our interest rate. And this is approximately 13.2 years. And that doesn't happen. You don't get 5.25% interest. They'll charge you 5.25% interest on loans, for sure. But they don't pay you that. What if he wants to triple his income? With the 2.25%. Now his multiplier, triple means 3. So once it's doubled, to get it up to triple doesn't take another 30 years. It only took another 18. Or, yeah. Okay, so this is similar to what happens where other models come up. What if the multiplier, let's call it m, is a positive fraction less than 1? Like 0 is less than m less than 1. Well, now this leads to exponential decay. Well, it's not really decay. Yeah, it's decaying, it's going up in value. This is the, if m equals 1/2, this leads to the idea of a half-life or carbon dating. Because like if we look at it in our compounded interest problem, well, what am I saying here? Like let's say we wanted smiley face, we wanted to end up having 1/2 of it. We ended up solving this. We found out if you don't know what k is, this is hard to explain. We get 1/2 equals e to the kt. If we look at the exponential curves, one half is back over here. X is less than 0. Or in this case, x is t is less than 0. We can't go backwards in time. The only other way to have that would be if it's negative. And right about here is t equals 1/2. And what, no, not t equals 1/2. Y equals 1/2. What's the t? Here, k is negative. So the multiplier, a multiplier less than 1 leads to exponential decay. Unless you have a way of going backwards in time, and then we could use this model. But until you discover time travel going backwards, this isn't going to happen. Look up time traveling into the future. You'll find it's interesting. It's some of the advanced laws of physics. If you go fast enough, though, everything around you is aging quicker than you. And so, like, you could go forward 300 years and only age 1 year. You can't go back. There's no going back. So let's see if I can find a good problem with that. So decay, we'll look at a decay one. Let's say we have 800 grams of a radioactive substance. Initially, and 2.5 years later, only 400 grams remain. Set up the model equation and find the growth rate. The rate of growth or decay, whichever one it is. So it looks like our starting value, initial, is 800 grams. Our final value is 400 grams. The time is 2.5 years. And we're building off of y equals y naught e to the kt. 400 is our final, 800 is our initial. We have e to the k times 2.5. This models it. That's our model equation. We'll divide by 800. And we get 1/2 equals e to 2.5k. When the left side is 1/2, that's our multiplier. We're literally finding the decay rate with a half-life. We take the natural log of both sides. One. And we divide by 2.5, we get k equals natural log of 1/2 divided by 2.5. Breaking this up, remember when we have division on the inside, I can treat that as subtraction on the outside. And ln of 1, log base anything of 1 is 0. This is negative natural log of 2 over 2.5. Oop, I'm rocking my camera. So I got negative natural log of 2 divided by 2.5. K ends up being negative. Now I use this one. Well, let's use this one up here. I want you to see it's the same. So natural log of 1/2 is 0.5 divided by 2.5 gets me the same value. These are the same. And what could we use that for? Well, we could figure out, let me give you time to finish writing that. Pause it for a second. Okay. So I've got, let's write down what we got again. Same problem. We started off with 800. We found K to be approximately negative 0.2772588872. The exact value was negative natural log of 2 over 2.5. When will we have, well, when will there only be 75 grams remaining? So we start off with 75, or we end with 75 grams. We start off with 800 grams. We have e to the kt. We know what k is. I'm going to use that. I'm going to leave it. I'll plug it in later. I'm going to solve for t. Divide by 800 grams. $75 over 800, that's 3 times 25 over 32 times 25. So this is 3 over 32 equals e to the kt. We take the natural log of both sides. And that goes to 1. We're solving for t, we divide by k. I've already done that last one. So I have this stored in the calculator. Already in calculator. Or you can do it at the end if you didn't keep it in there. Already in calculator. I'm going to do, I'll say parentheses, natural log, parentheses of 3 divided by 32, and parentheses. I'll end the parentheses again, divide by the denominator. 8.5. T equals 8.5, 3759, 3748. This was years. We started off going to 1 decimal place. T is about 8.5 years. So that's an example. Once you found K, oftentimes you don't know what the half-life rate is, the decay rate. Once you do find it, though, you can figure out how long it's going to take to end up with a specific value. Where do we use stuff like this? Have you heard of Chernobyl? Or the Tokyo nuclear plant? I don't know if Tokyo's actually spread out radioactive decay. Chernobyl blew up. The whole entire area is radioactive. They want to know how long will it be until Chernobyl is safe. So they knew how much they had a starting amount of radioactive material. They decide what the ending amount needs to be, and they can calculate how much time it is. And I forget what it was. It's really long. Those are the types of problems we do. And that's where they come up with. You'll see some fun ones in there for carbon dating. It's another form of radioactive decay, the amount of carbon-14. So carbon dating, I'll just describe it briefly. It is radioactive decay. What they do is they test, they calculate, they find starting and ending values of carbon-14. And they did this for a specific item. They started off when they knew how much carbon-14 was in there. A certain time later, they did it again. And they found, let's see, what's that value say? They end up getting the model y equals y naught e to the negative 0.0001216 t. And so this is the amount, where y naught is the amount present, amount of carbon-14 present in living plants and animals. When something perishes or dies, no more carbon-14 is created, and it starts decaying. Following that equation. And so the way they use this, they find bodies, or they find fossils, remains, something like that, and determine the amount of carbon-14 in it now. Which is our y value. They determine by what it is, determine initial amount by what it was. Like if it's a human skeleton, and based on whatever bones they have, they can figure out how much carbon-14 would, if someone just perished, how much should be in like your arm bone. Let's say they just found the arm bone, and they see how much it has versus what it does, what it should have had, and they have K. They can calculate T. Or how long ago the person, how long ago the creature, plant or animal, died. That's what carbon-14, carbon dating is. I'm sure there's a problem in there that gives you an example of it. Those are some fun examples of applications of exponential growth and decay. And that'll be it for chapter 4. I hope I have 9.1 ready for you tomorrow, but it will be ready this week coming up. Today is April 11th. My birthday's Monday, the 13th. My anniversary was yesterday. It's been a pretty good spring break. Peace.